So today we will be talking on accelerometer. And what is an accelerometer? This is like a acceleration sensor, like an acceleration sensor, and this sensor actually measure acceleration. Like while you are in a car and car suddenly accelerates. Now if you need to measure that how much is the acceleration, because from acceleration you can measure how much is the velocity, you can calculate actually how much will be the velocity and how much will be the what will be the distance traveled, right. So let us discuss on accelerometer or acceleration sensor, and this is our case study 2. Let us say we have this spring mass system. So this is a fixed plane, right, and then you have a spring and then a mass is hanging from it, right. Okay. Now you apply some amount of force. So let us say mass is m, you apply some amount of force, let us say F, and because of that the mass deflect, by x amount. Okay. Now what is the force on the spring? If the spring is k, then the force or restoring force is equals to kx, and at steady state, so this is the spring force, right, and at steady state the applied force, if the mass has an acceleration of a, then we know that F is equal to ma, right, and at steady state these two forces will be same and kx is equals to ma. Actually accelerometer or acceleration sensor uses this principle. So as soon as, now assume that this is our sensor, this spring is our sensing, it has the it is some kind of structure and it has the sensing element, etc. Okay, and this mass is actually applied with like some force is applied on this mass, or this mass is suddenly accelerated, and that we will measure with this sensor. So how we can measure? This is the same phenomena we will use, which we have been discussing from module 1 itself, right, that if we apply some amount of force, then there is this reflection, then we can measure the deflection, and accordingly we can measure that how much is the force or the acceleration. So here also this is the deflection, and this deflection is of the spring. So in our case, let us say if we, while we are using some kind of sensor, this deflection of will be of that particular membrane or cantilever, and accordingly we can measure the acceleration. And what will be the sensitivity? So sensitivity equals to x by a, per unit change in the acceleration, how much will be the change in the deflection, and that is m by k. This small m, capital M are same. Okay. So then if we get m by k ratio higher, then we get higher sensitivity. Okay. What are different technique by which we can actually measure acceleration? So one we have already seen during while discussing the pressure sensor, that is piezoresistive, So then what we will do, we will put some kind of piezoresistive element here in the spring. So as soon as some stress or strain is applied on the piezoresistive material, it will its resistance will change, and accordingly we can measure that how much is the deflection or how much is the force. And number 2 is like capacitive. So there will be some base plate, there will be some base plate here, and with that base plate we will measure that how much is the, let us say if this is another plate, the top plate, this mass is the top plate, then how much is the capacitance in between the top plate and the bottom plate, and accordingly we can measure that what is the distance or what is the deflection of the mass. Now let us discuss a bit about piezoresistive one. So let us say we have a structure like this. So this is like a membrane, that this inside plate is like a membrane, and this is in between these two, this cross region is like gap. Okay. So this is like a membrane or some kind of cantilever plate which can move or vibrate, which can deflect. So this cross region is a gap. Okay. So this is region, it is not connected. So this is like a flapper or a flapping wing kind of thing which can move up and down. Okay. If I draw the cross sectional image, then it will look like something like this. So this is the flapping part, actually this is the flapping part is moving, and this is the frame. This both are the part of the frame. I'm taking the cross section in this direction. So we have this. So this is the frame, and on between that, so this is called kind of seismic mass. This can be called as seismic mass. Now what we do, we put two piezoresistors, one piezoresistor here and another piezoresistor, let us say here. So one is on the moving part of the seismic mass junction, and another is the this is P sensing and this is P reference. So see, initially while the membrane is not deflecting, then PR and PS will have the same resistance, both are at the same position, and let us say they are fabricated similarly, so both are of same resistance. So here also it will, I will draw the PS. So this is the piezoresistor, sensing piezoresistor PS, okay, and this is the reference. So as soon as there will be some acceleration, or there will be some acceleration, like let us say this cantilever, now this is fixed to this to my hand, right. Now if my hand move up and down, accordingly this also starts vibrating, right, and because of that, if there is a piezoresistor, then there will be some stress or strain on that piezoresistor, and that will change its resistance, and that resistance change we will measure in compared to the PR or the reference resistance, because the PR or the reference resistance is at the frame, this is not on the moving part of the sensor, this is on the frame. So, this will be constant, this will not change, whereas PS will be changed. And the advantage of having this kind of reference resistor is, let us say there is some change because of the temperature or applied voltage or any other parameter which is not which is common to both of the case, like the reference resistor as well as the sensing resistor. So, those effects will get cancelled out, because if that because of the temperature, if the resistance is changing, then that will change similarly for both of them. So, PR and PS will increase or decrease by same amount for temperature, but the acceleration effect is only on the sensing element, because the reference element or reference piezoresistor is not moving at all. So, ultimately we can measure the resistance change at the sensing element and we can measure the acceleration. Now, while making the actual structure, I will just delete it, seismic mass. We need to package it, and in while packaging we use a bottom cap and a top cap. So, this is like the bottom cap and a top cap. So, bottom cap and top cap, and you see that this is the membrane, or this is the not the membrane, rather it is like the seismic mass which is actually moving. It is like cantilever, but the head is much in geometry, the head is much bigger than its anchor region. So, as it is moving, there is to get rid of stiction or any of in-use stiction or those kind of effect, what we can put is in the top cap or bottom cap, we put this kind of dimples or anti-stiction tips. So, even though it moves top and up, top and bottom, it will not get stuck to the top cap or to the bottom cap. And another point I would like to mention here is, if we are using capacitive technique, then we can measure the capacitance between the seismic mass and the top plate or at the bottom plate, and accordingly you can see that if it is moving down, so the gap between the top plate and the mass is increasing, whereas bottom plate and the mass is decreasing. So, we can measure that one side capacitance will increase, and other side it will decrease. So, accordingly we can measure that how much is the change in the capacitance or what is the deflection. So, that also can be done if we are using capacitive technique. Okay. So, now let us move to the second type of accelerometer, that is capacitive accelerometer, and here I am showing you this structure. I am showing you this structure which is a suspended structure. So, you see that there this is the substrate, this blue is the substrate which is silicon, bulk silicon. Then on top of that there is this sacrificial layer or anchor layer, this is SiO2. So, this pink side you can see here, this is SiO2 of 1 micron, and then we have the floating structure or actual proof mass, which we call proof mass, is the beam or the moving structure, that is again silicon. This can be polysilicon, also single crystal silicon, and that is let us say 10 micron of thickness. Okay. And then we have two different metal contacts. So, one contact is from the like this suspended structure, and another contact is on the substrate. So, substrate is fixed, right? Substrate is fixed, and on top of the substrate this membrane is vibrating, and in between them we can measure the capacitance, and we can measure that how much is the change in the capacitance, and accordingly we can measure that what is the acceleration. Now, for making this we start with a SOI layer or silicon on insulator. So, you see there are three different layers. Okay. So, first top one is the silicon layer, but in the middle or the sandwich layer is silicon dioxide layer, and the bottom is also silicon, which is like single crystal silicon. Now you see the basic difference. So all are silicon here, right? All are silicon. This is silicon. This is, sorry, not all are silicon, rather this is silicon, and this one is SiO2, and the top one is again silicon. But there are some specific differences between this the top silicon and bottom silicon. That you can see here that the thickness is not same. So the bottom layer is called, bottom silicon is called, that is the stubby, that is like the platform or the substrate. This is called handle layer. Okay, the bottom layer, bottom silicon can be called handle layer. And the top silicon is much thinner compared to the bottom silicon, so it can be 10 micron, 20 micron, whereas the bottom layer or the handle layer is like 500 micron. So this is called also device layer, and in between SiO2 is sacrificial layer. Another important point is this top silicon layer can be single crystal silicon or even polycrystalline silicon. If it is polycrystalline silicon, then on the SiO2 we just grow the silicon film. Okay, then it will be a polysilicon film. Whereas if we add another on the bottom silicon we connect, or on the bottom silicon we actually grow silicon dioxide, and then from top we actually connect another silicon wafer completely, we bond another silicon wafer, then we etch from the other side. So let us say this one was 500 micron, this is let us say 1 or 2 micron, and the top was also about 500 micron. Then the top silicon is etched till this point, so that it will become thinner, and this silicon will become like the device layer. Okay, so this, in that case, that silicon is single crystal silicon, because single crystal silicon wafer is if we are using a silicon wafer cut from a silicon ingot or single crystal silicon piece, then this silicon will be single crystal silicon. Whereas if it is grown using CVD or any other technique, then it will be like polycrystalline silicon, and this kind of silicon wafers are very much popular in MEMS device fabrication. Now we have discussed lithography in in module 3. There we saw that how we can make a pattern on the silicon or on any substrate using photolithography and e-beam lithography. And here you see that using lithography we have, from this structure we have etched the silicon according to our requirement or our design, and we have got this structure. And after that, if we dip this sample into buffer HF or BHF, then that will etch away the SiO2 part. That will etch away the SiO2 part wherever it is exposed. So all of these regions will get etched away, but whichever region is below the anchor, as this is much bigger. So here one point to note is this beams are much smaller than the anchor. Just for the drawing we have made it like that, but it is much smaller than the actual beam. So it is not in scale. Okay, so these anchors are much bigger than the beam size or this size or the proof mass size. Okay, and not exactly, actually the proof mass is much bigger, but there are holes. So through the proof mass, these holes are kept for that purpose, that the BHF solution can go in and it can etch all the SiO2 below it. So through these holes HF solution can go in and can etch away this material. So this region, let us say this region where SiO2 below this region, will get etched from this side as well as from this hole. Accordingly, SiO2 below this region will get etched from this hole and this hole, also from this hole, also these two holes also some amount will come, and also from this side. Ultimately at the anchor region only SiO2 will be left, all the other regions it will be gone, and we will get a suspended structure like this. And then we, using again lithography, we can make this metal contact at these two particular position. And this is the real optical micrograph image of the capacitive accelerometer, and here you can see that so there is this particular system we call laser Doppler vibrometer. So using that system the frequency of vibration can be measured. So as we know that all the structures have a resonance frequency, and what is that resonance frequency? Let us say I have this cantilever. Let us say I have this cantilever, then I bend it and leave it, then it starts to vibrate with a particular frequency. I deflect it and leave it, it starts to vibrate with a particular frequency, that is its natural frequency. Now let us say while we are actually vibrating, that means I am not leaving, rather the force itself is vibrating, I am giving a vibrating force. Then if this frequency, what is the applied force, that frequency and its natural frequency, if it matches, then it is called resonance, and in that resonance the amplitude is maximum. So let us say if I am applying some force and it is vibrating with some amount of amplitude, as I am changing the frequency, then at particular frequency the amplitude will be maximum, because then the natural frequency and the forced frequency are same. In that case amplitude will be maximum. Okay, so that is called resonance frequency. So this structure, while measured using this laser Doppler vibrometer system, where we use actually a laser source, and then using Doppler effect we can measure the how much is the vibration frequency of this of a particular structure. Using that system we got it 35.5 kilohertz, whereas if we while we calculated the effective mass of this particular suspended structure was at 0.10 to the minus 8 kg, and its stiffness, as we have seen in module 1 and 2, that we can calculate the stiffness for this all the 4 beams, and then like for a single beam then we can calculate it for all the 4 beams, right. And effective stiffness is equal to 304 Newton per meter. So this is K and this is M, and actually from this dynamic system, for the dynamic system we can show that frequency of a dynamic system or resonance frequency should be equal to 1 by 2 pi into root over K by M, and that is equals to 34.54 kilohertz. So according to our design and the material properties and other thing, it should come as 34.54 kilohertz, whereas while we measured we got 35.5 kilohertz. So 1 kilohertz it is off from its design frequency. And this is from the laser Doppler vibrometer, the actual like vibrating image, which is actually a kind of reconstructed image, and here you can see that the beams are much thinner than the proof mass, and if we see the frequency response, and you can see that initially there is some amplitude, which is like much lesser, about even below 15, and as we are switching the frequency it is almost same, but as we are increasing more and more the frequency, after certain frequency it starts increasing and it reaches a maximum at this point, and that is the 35.5 whatever we have got from experiment, right. So this is the peak frequency where or the peak or the amplitude is maximum. So this is our resonant frequency. This is our resonance frequency, that is about 35.5. And again, if we increase more than, if we increase our frequency or the forced vibration more than the resonance frequency, then again it decreases. So while the structure is under some kind of force or some kind of applied force, then what happens is this frequency changes. So initially the structure is this membrane or this proof mass is vibrated with some basic frequency or some forced frequency. As soon as some acceleration change occurs, then we will see that change in the frequency response, because its frequency changes, and accordingly we can measure that how much is the acceleration. Now let us discuss one of the in-plane accelerometer. So this in different context we have already seen this image, still I will draw it once more. So let us say this is the proof mass which is actually vibrating in plane. Now we measure the capacitor in between the fixed plates and the moving plates, or the or this membrane, right, or this proof mass. So this is the proof mass, and as as some force comes, as some acceleration or force comes, so let's say this sensor is put on this body. Now as this will move, and if it experiences some kind of change in the acceleration, and if it experiences any kind of change in the acceleration, then this structure will like move in this direction or in this direction, right. So this is in plane movement, and according to that the gap between the fixed electrode and the moving electrode will change, and according to that the capacitance will change. And by measuring, so this will be connected to an electronic circuit, and that will give an output voltage V0, which will be related to the change in the capacitance, which is in turn related to how much is the deflection or how much is the acceleration. So, and accordingly we can measure the acceleration using this kind of accelerometer.